So my name is Carl Berger and I'm going to talk today about plasma oscillations and plasmons. And I'm going to start out by just giving some physical insight into what's going on in these systems. And then I'm going to do a little bit of back of the envelope algebra to derive the plasma frequency. Derive might be too strong a term because really if you want a proper derivation, you're going to have to go to another source. You're going to have to look in a textbook or another online resource. But plasmons are very interesting these days, and plasma oscillations are interesting because this particular type, surface plasmon, has recently got a lot of attention in terms of making nano-optical devices. And so that's one of the reasons people are interested in this area. So what's a plasma, first of all? Well, we're mostly going to talk about metals, and a metal is a type of a plasma. Plasma is a gas of charged particles. And in a metallic plasma, it's a neutral plasma, so that on average there's the same number of positive and negative charges, not like I've drawn it. In a metal, you have the positive charges are screened nuclei that have the core electrons still bound to them, and then the negative charges are free electrons that move around. And if you think about what happens in such a neutral system is you can realize that even though on average it's going to be neutral, maybe over some short length scale, so if we just sort of draw a box in here, you might have a little bit extra negative charge, a little bit extra positive charge, and so that there will be occasionally some charge separation. So let's draw some charge separation happening here. And the charge separation gets at really what goes on in a plasmon, because in a plasma oscillation, because once you have a charge separation, you have a Coulomb force. Now in a plasmon, the positive charges, because they're nuclei, are quite stationary. The electrons move, so in this system the force is going to act to pull the negative charge towards the positive, just because electrons are so much lighter, so much more mobile. And as it moves, it's going to pick up kinetic energy. In fact, when it passes the positive charge, it's actually going to have the maximum kinetic energy, and then it's going to start slowing down because the Coulomb force is now going to be opposite in sign. And so it'll just come out here, turn around eventually, come back, and there you get the oscillation. Okay, it comes back and goes through. And the oscillation, you can think of oscillations in terms of exchange of energy. So the exchange of energy here is between an electrostatic energy, and a kinetic energy. Kinetic here. So actually the exchange happens twice per oscillation period. So you start out with electrostatic potential, you then transfer into kinetic potential, then back to electrostatic potential, and then back to kinetic, and then you complete the cycle back in electrostatic. So you go through two exchanges of energy in a single period. So that's the basic physical picture of charge separation followed by oscillation, and of course that oscillation isn't going to last forever. There will be a little bit of decay or loss, and so there will be a little bit of slowing down that will damp out eventually. Now in a more mathematical sense, you can look at the stored potential energy in the electrostatic system. But to do that, first you need to make a guess at the amount of charge and the separation of the charges. And so we'll just guess the electron charge, because these are free electrons that are moving. And the separation, the one that's most logical, is just the average separation of particles in the system, which we'll call S. And that'll be the cube root of the inverse density, particle density. So if you remember a little bit of your electricity and magnetism, the potential energy stored between two separated charges is going to be just Coulomb's constant times the charge squared over the separation. And if you remember your harmonic oscillator physics, so this is from classical mechanics, and by the way, I'm assuming that you remember electrostatics and classical mechanics if you've studied those. If you haven't, you need to catch up on that area to understand this. But in that case, the harmonic oscillator energy is 1/2 m omega. We'll call that omega p. That's going to be the oscillation frequency, x squared. So that's the standard form for the energy stored in the oscillator. Except I used x squared. That x should actually be an s squared. So stating these as equal is a little bit odd because it's clearly not a truly harmonic oscillator, because the force acting on these goes like 1 over the separation squared, and it's not proportional to the separation as it should be in a harmonic oscillator. So that's where this derivation is really quite rough. But it gives you the correct form, and it gives you the correct physical insight. And the result of a little bit of algebra is just that the plasma frequency scales with the square root of the free carrier density squared, charge squared, divided by the mass. And this is actually the effective mass, not the electron mass. But at this point we've ignored all sorts of other factors, so like Coulomb's constant has disappeared, and so in fact I'm going to replace that equality with just a little proportional to symbol. So it tells you that the plasma frequency, which is typically in the ultraviolet for metals, it goes up with the free particle density in the plasma. So that's plasma oscillation. Now, what's a plasmon? Well, plasmon is a single quantum of a plasma oscillation. So just like a photon is a single quantum of an electromagnetic oscillation, a single plasmon is a quantum of a plasma oscillation. The difference between electromagnetic oscillation and plasma oscillation comes down to this exchange of energy here. So in a conventional electromagnetic oscillation, you're exchanging energy between electrostatic potential and magnetic potential, magnetically stored energy, whereas in a plasma oscillation you exchange energy between electrostatic and kinetic. And of course there's also some magnetic fields formed by the current here, but it's the presence of this kinetic energy that's really quite different from what you're accustomed to thinking about in free space for an electromagnetic field. And this also relates to the concept of kinetic inductance, which we've talked about in another one of these videos. So with that, we'll finish for today. If you have any questions, please feel free to leave them below, and I'll do my best to answer them. Thanks.